Now that we know what directions will be part of our acceleration, let's return to our original task, which is to find the component of the acceleration of some motion r of t in each of these directions, the unit tangent direction and the normal direction. So just as a reminder, if we have some motion like this, right, our vector r prime is going to be pointing in the direction of motion. Capital T also points in the direction of motion, but it is a unit vector. And then our acceleration vector might be pointing out in some direction like this, and the unit normal vector is perpendicular to the unit tangent, and it is the other direction along which the acceleration vector r double prime has a component. So there's no third component of r double prime, and that's what makes this unit normal vector special. Okay, so let's find the component of acceleration in these two directions. So one way to think about this is, because r prime only has these two components, a component in the direction of r prime and a component in the direction of n, we can just name the length of each of these things. So let's name the length of the component in the direction of r prime. Let's name that a sub t. So this is for tangential acceleration. And the component in the direction of capital N, let's call that a sub n. So that's the normal component of acceleration. And this is achieving exactly what we wanted to do, of separating the acceleration into a direction that changes our speed and a direction that changes our direction of motion, right? Because the normal acceleration is changing our direction of motion, and our tangential acceleration is changing our speed. All right, so how to do this? Well, r double prime, right, the way that we have it written here, r double prime is just, you take the unit tangent vector, you scale it by this function a sub t, right? A sub t is a scalar, right? And that gives you this red component I've drawn here. We just need to add to it the part of the acceleration that points in the normal direction. So that's in the normal direction, so it's a scalar multiple of the unit normal vector, times whatever scalar valued function we need, which is what we're calling a sub n. One thing to note here is that a sub n is always greater than or equal to 0. It can never be negative, because the normal vector is always sort of pointing into the turn, and the acceleration also always points into the turn. That's kind of the definition of into the turn. So our function a sub n will always be positive. All right, so how to get a handle on these two functions, a sub t and a sub n? Well, it's not really clear at first, but one nice trick is to think about doing operations on r double prime and seeing what the result is on the right-hand side of this equation. One operation we could do is dotting r double prime with something. What should we dot it with? Well, I mean, there are only a few things to try. Let's try dotting it with r prime just to see what happens. So if we dot the left-hand side with r prime, we have to dot the right-hand side with r prime. So on the left-hand side, we get r prime dot r double prime. Now the dot product distributes over vector addition, so we can distribute this dot product. Also remember, a sub t is a scalar, so we can move it out in front of the dot product. So we get a sub t times the dot product of r prime. So I'm really falling down on writing all of my vector hats. I don't know if that bothers you or not. It doesn't bother me, but like, I know what I mean. So okay, so we're dotting r prime with t, right? We're distributing this dot product, plus, and then distribute our r prime to the second term. Again, we can move the scalar function outside, so a sub n times r prime dot n. Okay, now this looks bad at first, but remember, n is perpendicular to t, but that means n is perpendicular to r prime as well. That means that this dot product is actually 0. All right, so that leaves us with r prime dot r double prime. is equal to this tangential component of acceleration times r prime dot t. But remember, so r prime is perpendicular to the normal vector, but r prime is parallel to the unit tangent vector. So on the right-hand side here, if we use the geometric formula for the dot product, we get the magnitude of r prime times the magnitude of t times the cosine of the angle between them. But the angle between them, because they're parallel, the angle between them is 0, and so this cosine part is actually 1. So we get r prime dot r double prime equals this tangential acceleration times the magnitude of r prime times the magnitude of t. But remember, t is a unit vector. Its magnitude is always 1. And so now we can just solve this equation for the tangential acceleration. So it's the tangential acceleration, the part of the so the magnitude of the acceleration in the tangential direction is r prime dot r double prime over the magnitude of r prime. Now I did say the magnitude of the acceleration in the tangential direction, but that is not quite right, because notice that this dot product could be negative. So a sub t could be negative. And right, the reason that that is happening is, so if our tangent direction is like this and our acceleration is like this, right? This acceleration, this is how it looks when the tangential acceleration is negative, right? Because the component of the acceleration in the tangential direction is acting against our direction of motion. And so this is what happens when we're slowing down. And this is exactly the situation when r prime dot r double prime is going to be less than 0, because r double prime is pointing mostly away from r prime, right? So it does make sense that this dot product in the numerator could be negative, or it could be positive. So it's positive when you're speeding up, and it's negative when you're slowing down. Okay, so now so we figured out the tangential acceleration. Now let's see if we can figure out the normal acceleration. So remember, our strategy was to take r double prime and write it as some tangential acceleration times the unit tangent plus some normal acceleration times the unit normal. Okay, so, and we know what this tangential acceleration is. Now, right, that worked so well, dotting with r prime worked so well, right? You might think, well, look, the reason that worked so well is because we know that n is perpendicular to r prime, and so this first part dropped out. You might think, well, let's dot this with n, because now when we distribute this on the left hand, when we distribute our dotting with n on the right hand side, we're going to get 0 for this first part, and that's true. So n dot r prime, r double prime equals, right, here we get tangential acceleration times n dot t, and this is indeed 0, plus a sub n, and then we get n dot n. So things look really good at first. So on the left-hand side, we're just getting n dot r double prime. On the right-hand side, we're getting normal acceleration, and then n dot n, that's the magnitude of n squared. But n is a unit vector, so magnitude of n squared is 1, so this is just a sub n times 1. So this looks promising, but what is n dot r double prime? I mean, the problem is n dot r double prime, all we know about it is that that is our name for a sub n. So we've essentially proved that a sub n is equal to a sub n. That's not helpful. So, I mean, it's true, but it's not informative, right? So dotting with n turns out not to be so great an idea. If we want to have some slick way of figuring out what this normal acceleration is, we need another way to, we need some other operation to come up with that will give us information about this equation, right? So let's start over. So, right, the first thing we did that worked well is we dotted this with with r prime, which made this first piece 0. What could we do to get this, sorry, it made this second piece 0. What could we do to get this first piece 0? Well, dotting with n would do it, but that didn't help. Another thing we could do is take a cross product with something parallel to t, because cross product of parallel vectors is 0. So what's a vector parallel to t? Well, t, of course, but also r prime. So let's cross this. Let's cross both sides of this equation with r prime and see what happens. Right, what we're after is an equation for this normal acceleration that doesn't involve the unit normal vector, because the unit normal vector is messy to calculate frequently. So let's cross with r prime and see what happens. So on the left-hand side, we just get r cross r double prime. I see I've stopped writing my vector hats again, equals. So on the distributing this cross product, right? Cross products do distribute, and just like with dot products, scalar multiples you can move outside the cross product. So in the first part, we get our scalar multiple, which is tangential acceleration, times r prime cross t, plus, and now distribute our r prime cross to the second term here and move the scalar multiple out in front, and we get a normal acceleration times r prime cross n. Okay, now look, r prime and t, these are parallel. So cross product of parallel vectors is 0, so this is 0. All right, so now we're left with r prime cross r double prime equals our normal acceleration times r prime cross n. And you know, at first still this doesn't look so helpful because, I mean, it's true enough, but we don't know what n is, right? So solving this equation for a sub n won't be helpful because we'd have to calculate n. And that's what we're trying to avoid. Calculating n is frequently messy. So what could we do? Well, it takes some playing around to come up with this idea, but let's take the magnitude of each side. One reason this might occur to you as a good idea is because, well, if all we care about is a scalar quantity, a sub n, we should do something that produces scalars. But cross products are vectors, so how could you get a scalar from a cross product? You could take its magnitude. So on the left-hand side, we get the magnitude of r prime cross r double prime. On the right-hand side, right, if you have a constant times a vector, you're taking the magnitude of a constant times a vector, that is the absolute value of the, I keep writing a double bar, that's the absolute value of the constant times the magnitude of the vector, right? But we know that we observed way at the beginning that a sub n is always greater than or equal to 0, and so when we move this scalar multiple out in front and take its absolute value, well, it was already positive, so the absolute value does nothing, and we just get a sub n. So a sub n times the magnitude of r prime cross n. And remember, we're hoping to get rid of n, because actually calculating n would be a big pain. So let's use the geometric formula for this magnitude of a cross product. The magnitude of a cross product is the magnitude of the first factor times the magnitude of the second factor times the absolute value of the sine of the angle between them, right? But wait a second. So first of all, the magnitude of n is 1. Second of all, right, remember the general situation. We have r prime parallel to the curve, and we have n perpendicular to the curve. So the angle between these two vectors is pi over 2, and so the sine of pi over 2 is 1. So putting this all in our equation, we get the magnitude of r prime cross r is the normal acceleration times the magnitude of r prime times 1. So finally we can solve for the normal acceleration. It's the magnitude of r prime cross r double prime over the magnitude of r prime. Okay, so notice this has a really kind of pleasing symmetry with what we got for the tangential component of acceleration, which was r prime dot r double prime over the magnitude of r prime. Right, so the difference between the tangential and normal component is whether you're using a dot product or a cross product. That's kind of nice. Also notice something else. This formula for the tangential acceleration, this is just the component, the scalar component onto r prime of r double prime. And that makes perfect sense, because if we have our r prime vector like this and r double prime like this, then right, the tangential component of acceleration, that was exactly what the scalar you get from squashing r double prime onto r prime. So, and that is what we earlier called comp r prime r double prime. So it's not really a surprise that we get this for the tangential acceleration. The surprise is that the normal acceleration is such a nice formula.